Why was hybridization theory developed? Why is this theory so important? And how does it allow the chemist to envision a molecule in 3 dimensions? In this chapter, we will explore some of the reasons why hybridization theory was developed. A student's ability to take a 2-dimensional molecule off the blackboard during lecture and fold it into 3 dimensions, or envision a molecule in 3 dimensions from a page in a book, is arguably one of the most essential skills when learning chemistry. The chemistry student who has the ability to visualize molecules in 3 dimensions is rewarded with a better understanding of chemical properties, physical properties, and most importantly, the ability to predict chemical reactivity. Understanding how atoms within molecules are oriented in 3 dimensions requires an understanding of hybridization theory. From simple molecules such as ethanol to more complex molecules such as the highly toxic tetrodotoxin, the concepts of hybridization are the foundation to our understanding of molecular geometry. However, looking at a 2-dimensional Lewis structure of a molecule affords much information to the scientist. For example, the overall connection of atoms within the molecular formula. After all, different structural and geometric isomers can be imagined from relatively simple molecular formulas. To introduce the concepts of hybridization, we will first focus all of our examples on the carbon atom. The basic principles discussed for the carbon atom can also be applied to other elements, which are explored in later sections. A carbon atom has 6 electrons in the following configuration: 1s2, 2s2, 2p2. The relative energy electron configuration diagram is another way to visualize where the electrons are located. Each arrow in this diagram represents one of the individual electrons of carbon. However, only the valence, or outermost electrons, are responsible for bond making and bond breaking. Thus, we can ignore the inert, noble core electrons, which we can represent here as the helium element. This abbreviated electron configuration quickly allows one to ascertain that there are 4 valence electrons. It would appear that there are only 2 unpaired valence electrons capable of forming covalent bonds, one in the 2px and one in the 2py orbital. However, it is well known that carbon forms a total of 4 covalent bonds to attain full valency. Thus, all 4 valence electrons must be involved in bonding. Hybridization theory was developed in order to better explain the 4 observed bonds of carbon. In addition, the hybrid model best explains overall molecular geometry of carbon. In other words, bond angles in 3 dimensions can be predicted. The possible hybrid combinations for a carbon atom are sp3, sp2, and sp, and are explained in detail in subsequent sections.